Alright, let's talk about Chapter 6, in which we will be talking about air-sea interaction. So this is how the atmosphere interacts with the ocean. So let's take a look at that. And so what is air-sea interaction? This is basically when changes in the atmosphere happen, it causes a change in the ocean. Now do keep in mind that any changes that occur in the atmosphere will make a change in the ocean, but it will be delayed. So, for instance, whenever we talk about climate change and we talk about increasing the carbon dioxide concentrations in the atmosphere, it has a delayed effect in the ocean where the carbon dioxide will stay in the atmosphere for a little bit before getting absorbed into the ocean. So there is a delayed effect there. But essentially, the cycle of air-sea interaction starts off with solar radiation hitting the Earth's surface. And when it hits the Earth's surface, it creates winds due to differences in temperature. And then when you create winds, those winds then interact with the ocean and they create currents in the ocean. And so the variations in solar radiation create the differences in pressure and density that create currents and waves in the ocean as well as in the atmosphere. So let's look at some different types of air-sea interactions that we can have. You can have your solar radiation coming in, and when that solar radiation hits the surface of the water, it heats up the water, which then creates evaporation, and that evaporation leads to water vapor escaping into the atmosphere, which then will create clouds, which then eventually, over time, will create rain, and so then that will rain onto the ocean. And then you have the wind. So when you have the difference in temperature, you create wind, and that wind then pushes along the ocean surface and creates waves. And sometimes if that wind is really strong, as it's going over the wave, it creates what's known as sea spray. So it basically aerosolizes the water and salt and whatnot, and it throws it up into the atmosphere. Let's see, what else is on here? Plankton can also use the incoming sun that enters into the ocean. And then you can also get turbulent eddies in the ocean from the solar radiation entering into the ocean. So there's just a number of different things on here that is considered air-sea interactions. So we'll talk about solar radiation variations at this point. And as you can tell, not everywhere on the Earth's surface gets an equal amount of solar radiation. Definitely the equator gets more solar radiation than the polar regions. The polar regions tend only to get a lot of solar radiation during the summertime, and during the wintertime they get far less solar radiation. And the equator tends to get a lot of solar radiation in the summertime, and it definitely does get a lot during the wintertime, but it's decreased, which is the reason why it's winter, so it gets a little bit cooler. As you can tell on this image right here, the Earth is tilted at a 23.5 degrees from straight up and down, and so that shows that not everywhere on the Earth experience summer at the same time. So if we go to the next slide, you can see that depending on where the Earth is at within its orbit around the sun will determine whether you're in spring, summer, autumn, or winter. So, and it also depends on what hemisphere you're in. So, for instance, this slide right here shows you the northern hemisphere. So, whether you're in summer or winter during the northern hemisphere will then be the opposite for the southern hemisphere. So, on the left-hand side there, you can see that the Earth is tilted towards the sun, which is known as the summer solstice, and that means that the northern hemisphere is experiencing its summer, while the southern hemisphere is experiencing its winter, because you can see that the southern hemisphere is pointing away from the sun. And so that's a lot like what we're experiencing right now here in Hawaii. Right now we have our summer. We are just past the peak of our summer. Our peaks usually are in August and September. We just entered October, so we should be dying down in terms of the amount of heat, and we should be switching over to what's known as an autumn equinox. So that means that we're switching over to autumn. I can't remember. It's sometime in mid-October when we have our autumn equinox. And that's when you'll start to see that the Earth is no longer, the axis of the Earth is no longer pointing towards the sun, but it's kind of halfway around to the point where you have your winter solstice, which is sometime in December, I believe. And that's when the Earth, the northern hemisphere, is tilted away from the sun. And that's when the southern hemisphere is tilted towards the sun. So southern hemisphere is experiencing their summer, while northern hemisphere is experiencing their winter. Okay, and then vernal equinox is just when we hit springtime, and the spring and the autumn, the Earth is tilted either to the left or the right of the sun, which means that the northern hemisphere and the southern hemisphere are getting about equal amounts of solar radiation at that time. So if we look at the next slide here, if you look at the global heat budget of the Earth's surface, you can see that the region in red definitely gets more solar radiation, and so there's heat gained. So overall, the overall average, there is more heat being absorbed at the Earth's surface near the equator than it is at the poles. At the poles, you can see there's a heat loss. So there isn't as much heat being absorbed into the Earth's surface at the polar regions compared to the equator. So you can so that would suggest that heating across the globe is not equal. There's no uniform heating. It changes depending on where you're at on the Earth's surface. So if we look at solar footprint, this is just implying at what angle is the solar radiation coming in, because this will depend on whether you're at the equator or if you're at the polar regions. Because if you're at the equator, and if we just use the image on the right hand side here, and you look at the flashlight and it's pointing, we'll just say that the sun represents a flashlight, and you're pointing it at the Earth's surface. At the equator, the curvature of the Earth is far less than it is at point B in the polar regions, where you experience much more curvature to the Earth's surface. And when that happens, you lose more heat to deflection. Right? So at point B in the polar regions, a lot of that solar radiation is being reflected back into space, and it's not actually getting absorbed by the Earth's surface. Whereas at point A, near the equator, almost all of that solar radiation is getting absorbed because it's not getting deflected, because it's basically overhead. There's no deflection. at that point. So let's look at this absorption and deflection that I was just talking about. So on the left-hand side there, you see a bunch of numbers in yellow. Just worry about the numbers in yellow. Don't even bother trying to understand the numbers in red, because those are something completely different. But if we just focus on the numbers in yellow, and we look to see, okay, if we have 100% of the light coming into the atmosphere from the sun, 19% of that will be absorbed by water vapor, dust, or ozone. So it doesn't make 19% of that does not make it to the Earth's surface. Another 4% of that will be absorbed by the clouds. So that's already, what, 22, 23, 9, 10, 11, 12, 13, 23% that's lost to objects in the atmosphere before it gets to the Earth's surface. And then finally, another 46% actually does make it to the Earth's surface and does get absorbed by the Earth's surface. But if you look at the arrows to the right of the 46%, you can see 8% is deflected back into space because of backscattering. So that's pretty much just particles in the air that the solar radiation hits that particle and bounces off of it and goes back into space. Then another 17% is reflected by clouds. So it's especially if they're white clouds. If they're gray clouds, that number goes down a little bit. And then also another 6% is reflected by the surface of the ocean, either the ocean or something light in color. So yeah, that pretty much should equal to about 100%. As you can see, almost a little bit over half of the amount of solar radiation that enters the atmosphere is either absorbed or reflected. So only 46% actually makes it to the Earth's surface. Now, albedo is just the amount of radiation that is reflected back into space. So that's the percentage of radiation reflected. And depending on the type of material, certain ones will reflect more than others. So for instance, light-colored materials like white or yellow, those particular colors will tend to reflect more sunlight than darker materials, say black, or anything that's black or blue. Those really dark colors will tend to absorb more material. So in this case, the clouds, white clouds in particular, tend to reflect more solar radiation than the darker gray clouds do. And then as well as ice and snow will have a tendency of reflecting more solar radiation than, say, the ocean or land. So let's look at this image again. Now the numbers on the left-hand side, the yellow numbers on the left-hand side, the 19% that's absorbed by water vapor, dust, and ozone, and the 4% that's absorbed by clouds, that is not albedo. That's just straight absorption of the sunlight. The numbers on the right-hand side, though, the 8, the 17, and the 6, those would all be numbers or percentage numbers related to albedo. So anything that is reflected, not absorbed, is your albedo number. So again, when you compare ice and snow and white-colored clouds versus land and the ocean, those ones will reflect more solar radiation. So if we look at different points on the Earth's surface and we look to see at the angle at which the sunlight comes in to hit the Earth's surface, you can see that as the angle decreases, so when you get up to the polar regions where the angle is at about 5 degrees, which means that majority of the sunlight coming into the Earth's atmosphere and getting down to the Earth's surface, a good 40% of that radiation is being reflected back into space. And this is the elevation of the sun above the horizon. So at the polar regions, if you think about standing, let's just say on a glacier, and you're looking at the horizon, the sun is only at 5 degrees above the horizon. Whereas if you look at the 90-degree side, that means that if you're looking at the horizon and you're standing at, say, the beach here in Hawaii, the sun would be directly above you. And so in that case, only 2% of the radiation coming down is actually reflected. So there's a huge difference between whether you're at the polar regions or whether you're, say, here in Hawaii. And that's also the same for the absorbed radiation. So here in Hawaii, majority of that radiation is absorbed either into the water or in the land. And in the polar regions, you can see that a lot less of that radiation is absorbed. So when that radiation is absorbed into the land or the water, it's heating up the surrounding environment. So that's why here in Hawaii we tend to have really hot summers, because a lot of that radiation is absorbed into the land, versus in the polar regions you're only getting about 60% of that radiation absorbed. So it doesn't feel as warm as it does over here. So let's look at this next slide here, because this one tells you where the different layers of the atmosphere are and what the temperature is at that layer. So on the left hand side there, at sea level, if we start to go up, you can see that it slowly starts to decrease in temperature until you get to the tropopause. So between the tropopause and sea level, that area is known as the troposphere. And this is the atmosphere in which we are surrounded by all the time. This sphere is warmer in temperature unless you get up to the top of it where the tropopause is at, and that's where you get really cold temperatures. Jet planes, when you go traveling to the mainland or to any international destinations, those commercial aircraft will travel in the tropopause region. So that's why it's fairly cold outside when you're in the plane, and they have to pressurize it to make sure that the warmth within the plane stays in. Let's see. Generally speaking, clouds tend to be within the tropopause, or the troposphere, I should say, at about 1 kilometer up from sea level. And you can see some of the other common things like parachuting is around 6 kilometers. Hot air balloons tend to get up to 2 kilometers, and those single propeller planes can get up to 4 kilometers. But your commercial jets will get up to 10 kilometers. And then if we go a little bit higher, if we go past the tropopause, you can see that the stratosphere, which is the next layer, starts to warm up just a little bit. Not too much, but just enough to be warmer than the tropopause. But it definitely doesn't go past 0 degrees. So it is cold, it's just less cold, if you think of it that way. And this is typically where you will see those really fast jets that the military use, the ones that go supersonic and whatnot. This is also where the ozone layer is at. So this ozone layer protects us from solar radiation, from getting too much solar radiation at the Earth's surface. So I think we'll get into talking about the ozone layer in chapter 16, 15, 16, whichever one climate changes. But essentially, the ozone layer reduces the amount of radiation that comes down to the Earth's surface. And if there were a hole in the ozone layer, such as there is over Antarctica, it's allowing all of that solar radiation to come down to the surface, which is kind of bad because a lot of the ice on Antarctica is melting at the moment because of that hole in the ozone layer. But we'll talk about that in more detail later on. And then if we go up to the very top of the stratosphere, you get the stratopause. So in between each sphere, there's going to be a pause. So you can just think of it as like an area where it changes into the next sphere, right? And so after the stratosphere, you get the mesosphere, which further decreases in temperature. It goes probably down to negative 90 degrees Celsius. And then you have the mesopause after that. And this is above the mesopause in the thermosphere is where you get the aurora borealis, or the northern lights. And as you go further up to about 1,000 kilometers, you get into what's known as the exosphere. So this is basically like the very edges of our atmosphere. The air is almost non-existent at that point. There's very little oxygen up there, and it's pretty cold out in space. So this is typically where you'll see your satellites and your spacecraft floating around, and there's definitely much less gravity affecting those items up there versus down at sea level. All right, so let's talk about convection. This is just a cartoon schematic of a convection cell, but this is how air circulates in our atmosphere. And if we just think about it in this closed room, and let's just say it's wintertime, the air outside is very cold, and so this person turned on their radiator to heat up the room. So over by the radiator, it's heating up the air over there, and that warm air rises. So no matter what, if it's warm air, it's always going to rise. And it can't rise up very much more, so it follows the ceiling over towards the window. And once it gets to the window, it cools down. And once it cools down, because there's no radiator over there, the air on the outside is penetrating through the walls, cooling down the air, and as that air is cooling, it sinks. So no matter what, whether it's in the ocean or in the air, a warmer temperature air or water will rise, and a cooler water or air will fall or sink. And so that cool air then sinks and can't just keep going, so it follows the floor all the way back to the radiator, where it heats up again, and then it rises. So it's a continuous cycle of the air heating and cooling, and it's creating this circulation of the air around the room. So that's how eventually you'll get the room warm, but or cold if it's during the summertime. Okay, so that circulation cell is essentially what happens in our atmosphere all around the world. So in our atmosphere, the water vapor also affects how circulation occurs. So the amount of water vapor in the air will depend on the temperature. So in warm air, which we have here in Hawaii, that our air holds a lot more water vapor. Versus if you go to Canada or Alaska, the air up there is very cold, and when you go outside in Alaska, that air is much drier. It doesn't hold as much water vapor as it does over here in Hawaii. And because of that, the density differs. So when you have warm, moist air, you'll tend to have less dense air, right? Because those air molecules are moving around really quickly because of all the energy it's getting from the warm temperatures. And even though it holds more moist air, there's still more space in between the air molecules and the water molecules. So it's not as dense as cold air, where those air molecules are slowing down. There's not a lot of energy coming from the temperature of the air. And so those air molecules are sitting closer together. So the spaces in between the air molecules are closing up. Therefore, it's more dense. So there's not a lot of space in between the air molecules. So let's look at this on a much larger scale. So on this slide here, you'll see Earth's surface in green. And then you'll see on the right-hand side, you'll see this area of warm rising air. This can be either by the equator, where it's warmer. And you'll see that the air near the Earth's surface is getting warmed up. It's also collecting water vapor, and it rises. Okay, so those molecules are farther apart, so that it's less dense. And then as the air travels along the upper troposphere, where it's cooler, it starts to cool down until it gets to a point where it's cold enough that it's going to start to sink, because the molecules have compressed together and there's not a lot of space in between them. So that air becomes more dense, which then starts to sink. So in these areas where you see cold air sinking, these are known as high pressure areas. These are associated with cooler, drier air, so you tend to have clear conditions, not so much rainy conditions. So when you look around the world, when you see these high pressure areas, you tend to see deserts, and I'll show you that in a couple of slides. But when you look at the warm air rising side, these tend to be low pressure areas, because that air rising is also taking water vapor with it. And so when that water vapor goes up into the upper atmosphere, it's cooling as it comes up. And as it cools and comes up, it condenses and creates clouds. So typically in these low pressure areas, you tend to see a lot of rain and a lot of storms. Okay, now let's think about this hypothetically, because in the last slide, I showed you that convection cell that it was creating between the low pressure and the high pressure areas. But if our Earth was not spinning and we just had a planet that was just floating in space, that convection cell that I was showing you would extend from the polar regions all the way to the equator, because there's no rotation. And you would have uneven heating of the solar radiation coming in. So all of that solar radiation would be hitting the equator, and very little of it would be hitting the polar regions. So you would have a low pressure at the equator, where warm, moist air is rising, and it would travel all the way to the polar regions, where then it cools down and it sinks. And then you would have a very dry, cool region, which is a high pressure over there. So this is just hypothetically if the Earth was not spinning. But we know that our Earth is spinning. So what ends up happening is you get these different regions of high and low pressure areas. And so when around the equator at the 0 degree latitude line, and if you go up from 0 degrees, if you go up to 30 degrees, that region right there is known as your Hadley cell. It is a convection cell that is created because you have a low pressure area at the equator. So warm moist air rises at the equator. It circulates north and south from the equator, and it comes down at the 30-degree latitude line, where it has cooled off, it has condensed, and it has dried out, and that air comes down and creates a high pressure area. So that region between 0 and 30 is known as your Hadley cells, Hadley circulation cells, right? So at the 0-degree line, this is where you have your low pressure. So there's a lot of rain and a lot of clouds at the equator. It's also known as the doldrums because of how much rain and how turbulent the water can be within this area. Sailors have nicknamed this region the doldrums. And we also have trade winds within the Hadley cell circulation. So their trade winds start from the northeast and they travel down and are down towards, I guess, the southwest, and then continue traveling towards a western direction. So the winds in particular are named for where they're coming from. So in this particular case, your trade winds come from the northeast. In the southern hemisphere, they come from the southeast, but they're still trade winds. And then between 30 degrees and 60 degrees latitude, this is what you would call your Ferrel cells. All right, so your Ferrel circulation cells, those are rotating in a clockwise direction, whereas your Hadley cell is circulating in a counterclockwise direction. So at your 30-degree line, you have a high pressure system, whereas at the 60-degree line, you have a low pressure system. So you have a lot of clouds and rain up there. Whereas your 30-degree latitude line with your high pressure, that has no rain. It's very dry and very clear. So that's typically where you'll see deserts at. And then where at the equator, you'll tend to see tropical rainforests. And then at the polar regions at your 60-degree line, you'll tend to see a lot of glaciers and a lot of ice. And then once you get past the 60-degree latitude line, this is where you have your polar cells, and those rotate in a counterclockwise direction. So they match what's going on near the equator, except it's colder up there. So in between 30 and 60 degree, your winds that you have over there are the westerlies, because they come out of the west and are traveling towards the east. And then in the polar regions, you have your polar easterlies. So they start off in the east and they are traveling towards the west. Okay, so now because of the Earth spinning, you can have changes in Coriolis depending on where you're at around the world. So definitely near the equator, you'll experience much larger velocities than you would at the polar regions. And that's because the amount of time, I guess you could say, for a particle at the equator to rotate all the way around versus the amount of time it takes a particle to rotate near the polar regions is far greater. So the particle at the equator has to travel a further distance than the particle at the polar region. So because of that, the particle at the equator experiences more Coriolis. And it's much stronger, because you can't have two particles on the Earth, one at the equator, one at the polar regions, traveling at different speeds. At different rates. Okay, they all have to travel around as Earth is rotating. They have to travel at the same time. So in order to do that, the particles at the equator have to travel faster, in order to keep up with the particles at the polar region. Sorry if this is a little confusing. Please let me know if you don't get that. But essentially, just think if you have a string and you're rotating it around, the end of the string would be rotating faster because it has to keep up with the part where you're holding it at. I don't know if that didn't clear it up, I'm sure. But we'll try to see if you can get it. And email me if you need any help understanding this concept. So what you can see is at the polar regions, it's 0 kilometers per hour. And that's because it's not, as the Earth is rotating, if you put a particle right at the very top of the North Pole, it's not traveling anywhere. It's not rotating any distance. It's just spinning in the same spot. So that's why it's not moving at any rate. Versus if you have a particle at the equator, it has to travel much faster to keep up with all the other particles. Okay, so now let's talk about the difference between weather and climate. So when you watch the news, if you guys watch the news, and they'll at some point during the news broadcast, they'll switch it over to the weather report, and they'll tell you, okay, so today the weather is going to be sunny. If it's here in Hawaii, it's sunny all the time in Hawaii, practically. But when they talk about the weather, they're talking about daily observations of atmospheric conditions at a given place and at a given time. So the weather here in Hawaii, generally speaking, is going to be sunny and warm compared to the weather in Alaska, where it's typically going to be rainy and cold. And it's going to change on a daily basis. So not every day is warm and sunny. We've this year had a number of days that were cloudy and rainy here in Hawaii. And that's partially due to La Nina conditions, which we'll talk about a little bit later. But yeah, so given that, the weather's not always going to be the same, even in that given place. It could change on a regular basis. Compared to climate, which tends to be a much more longer term average of the weather within an area. And so here in Hawaii, on average, on a long-term average, we tend to be much warmer and sunnier than other parts of the world because we are closer to the equator. And when you compare us to Alaska, Alaska will tend to be much colder and much more cloudy compared to us over here. So those are just different terminology, so don't get the two mixed up, all right? So wind movement, when we look at our high and low pressure systems, you can see that and this is in the northern hemisphere now. If we look at the southern hemisphere, it's just the opposite of this. And so our high pressure systems will be rotating in a clockwise direction, which means that air is coming down, right? So remember, this is cold, dry air coming down from the upper atmosphere down to the Earth's surface. So that cold, dry air is coming down in a clockwise fashion, or what's also known as an anticyclonic divergence. Or divergent, I should say. So basically the air is moving away from the center, right? Versus our low pressure system will be known as a cyclonic convergent, and the wind will be moving in a counterclockwise direction. And it's convergent because the air is converging into the center of this swirling mass. And remember, this is warm air rising, okay? So you have warm, moist air rising, which will create a lot of clouds. So typically when you are looking at that weather report and the weather whether a person is saying, oh, we're going to have rain in the forecast. Well, that person is just saying that, okay, there may be a low pressure system somewhere above us, and that low pressure system is creating clouds, which then generally produces rain. So let's move on. So that's the different movement types of wind in the atmosphere. But here in Hawaii, we have breezes. Okay, we have different breezes. We have onshore and offshore breeze, or what your textbook likes to call sea and land breeze types. So during the daytime, we have what's known as a sea breeze, or onshore winds. And that's essentially when the land is warming up more so than the ocean. So the land during the day will absorb more radiation than the ocean, and so the air over the land will rise. And since we're here in Hawaii and our air is very moist because we're next to the ocean, that air will pick up all that moisture and it will travel offshore, so to over the ocean. And once it goes over the ocean, it will start to cool down because the ocean is relatively cooler compared to the land during the daytime. So as that air cools off, it'll eventually sink, cool off, sink, and then travel back onto land. So that's known as onshore breezes. So this is typically either in the morning or midday, and that's when you're at the beach. The breeze tends to feel very nice because it's cooler. But then as the day wears on, this onshore breeze will be picking up more and more water. Okay. And so then at nighttime, later at night, when the land cools off, you tend to have what's known as a land breeze or offshore winds. And so this basically just reverses. And so the land cools off quicker than the ocean does at nighttime. And so the air over the ocean is warmer. And since it's over the ocean, it's picking up a lot of moisture. And it travels over land where then it cools off and sinks and then starts to travel back out towards the ocean. So that's why at nighttime you tend to feel nice cool breezes coming into your window, and that's because you have this offshore breeze. All right, so storms are atmospheric disturbances that are characterized by strong winds, rain, thunder, and lightning. So not all storms will have thunder and lightning. Majority of them will tend to have varying degrees of winds, and majority of them will have rain. And the more severe ones will have all four of them: winds, rain, lightning, and thunder. And you'll have different air masses too. So as the air is traveling around the world, it will pick up moisture and it will lose moisture, and it will warm up and it will cool down depending on where it's traveling at. And these air masses will tend to interact with each other, and they are typically characterized by large volumes of air that are defined by the area in which they are formed at. And so you'll tend to see polar air masses, tropic air masses, dry air masses, and moist air masses. And so if we look on this next slide here, in the continental US, you tend to see a lot of these air masses interacting with each other. And so depending on where you're at in the US, continental US, you'll experience different air masses. And when you have two air masses that are interacting with each other, that's when you can create some pretty gnarly storms. And so when, let's just say, in the what is that? The East Coast side, they tend to experience some pretty heavy snowstorms during the winter time, and that's typically when that maritime polar air mass on the top right hand side there drops down and interacts with the maritime tropical air mass, and either the maritime polar or the continental polar will come down, interact with the maritime tropical, and that's when you tend to see a lot of storm activities, as well as in the Midwest when they have a lot of tornadoes. That's typically when you see a warm air mass interacting with a cold air mass, and those typically can create some pretty nasty storms. But you can also experience fronts when these air masses interact with each other. And so you can get a cold front when you have a cold air mass interacting with a resident warm air mass. So this cold air mass is coming down and it's interacting with the resident warm air mass, and it tends to create some pretty large storms that typically will have thunder and lightning. They will be very strong, and most likely won't last more than a day or two. They tend to be short-lived, but they dump a lot of rain all at once, because as you can see, that warm air mass rapidly rises above the cold air mass, and creates this very large cloud, rainstorm cloud. Whereas if you have a warm front, that's where you have a incoming warm air mass interacting with a resident cold air mass, and that warm air rises ever so slowly to create a very gentle rainstorm. And this rainstorm typically doesn't have lightning or thunder, but it can last for a number of days. So those are the differences. Here in Hawaii, our air typically is warm normally, and so sometimes we'll have a cold air mass coming down from Alaska that will interact with our air. So we tend to see a lot of cold fronts here in Hawaii. So you'll see a lot of rainstorms that pop up one day, and the next day it's super sunny and not overcast whatsoever. And so when you see those types of rainstorms that come by, they tend to be cold fronts. They typically will dump a lot of rain all at once too. Alright, so the jet stream is a narrow, fast-moving, easterly flowing air mass. And so this air mass sits between the Ferrel cell and the Hadley cell. And this occurs around 30 degrees where you have your high pressure system. And this is in the troposphere. And this is a very fast-moving air mass. So like when you are traveling from Japan to Hawaii or to the continental US, airplanes will typically tend to use the jet stream to increase their speed because it is very fast moving, and they tend to cut down the travel time of that flight. So if any of you guys have been to Japan and you've come back, typically that flight will be a little bit shorter than the flight going to Japan. So from Hawaii to Japan, typically you'll experience anywhere from a 8 to 9 hour flight going from Hawaii to Japan. But when you're coming back to Hawaii from Japan, that typically tends to be a 7 to 8 hour flight. So that jet stream really does cut down the flight time by as much as an hour, sometimes even more, depending on how fast the plane is going. But you can see at the 60-degree latitude line, there is another jet stream, which is known as the polar jet. But this particular one is a little bit more rough. It's not as smooth sailing as the jet stream because it is in a low pressure system. So it tends, in that particular region, it tends to be more cloudy. It tends to have more rain. So in that case, even though it is a polar jet that's going in the opposite direction, it is a westerly flowing air mass. If a plane were to go in there, it would be kind of bumpy. So don't recommend it. Tropical cyclones are basically just hurricanes if you're in America, or they are typhoons in Asia, or if you're in India, that would be known as a cyclone. So all three of those, cyclones, hurricanes, and typhoons, are all the same word for essentially just the same atmospheric disturbance, which is just a giant storm. Okay, this type of storm is a low pressure system, so it is rotating in a counterclockwise direction, as you can see by the red arrows. This type of storm tends to have an eye, which is just in the middle of the storm, is an area where it's calmer. There's not a lot of turbulent winds within this area because of the rotation of the wind. It creates this middle section that's calm. So if you guys have ever heard of the eye of a hurricane, that's really calm and whatnot, that's what it is. Everywhere around it tends to be turbulent. So as the storm is spinning, it's picking up warm, moist air that's pulling it up into the cloud structure there, as depicted by the blue arrows. And as it rises, it cools and condenses and creates clouds. So you see that cap on the top there. It's not only insulating the storm, so it's keeping that warm air within the storm, but it's also creating rain, a lot of rain. Okay. So when we look at the different types of storms, last month we experienced quite a few. Well, not last month, I should say. In August, when school started, we experienced a couple of hurricanes that may have been one in particular, Hurricane Lane, that was got a little close to us, right? But in the end, it veered off. But when they were talking about, oh, it's a Category 4, oh no, it's downgraded to a Category 3, oh no, it's now down to a tropical storm, what does that mean? And so it just, when the officials announced that, okay, there's a hurricane and it's a Cat 3, it's just dependent upon the wind speed. So in this particular classification scheme, what is the maximum sustained wind speed? So when the maximum sustained wind speed is less than 38 miles per hour, it's known as a tropical depression. So the winds are pretty fast because on any given day, normally, the winds generally are between 5 to 10 miles per hour. So this is triple that normal wind speed. And during a tropical depression, you tend to see a lot of clouds and a lot of rain, but nothing that could cause a lot of damage, right? And on the image on the right-hand side there, you see a tropical depression is akin to somebody riding a bike. So it's not very fast at all, the wind speed. And this is all just the wind speed now. And then when you have a tropical storm, that typically tends to be anywhere between 38 miles per hour and 74 miles per hour. So that is akin to, say, a motorcycle or somebody driving a vehicle. So those wind speeds are a little bit more faster, and the tropical storms tend to bring a lot of rain. Some of them can have lightning and thunder, just depends. But nothing too bad. Typically, you don't see that much damage to a majority of the property during a tropical storm. Majority of the damage occurs when you have tropical cyclones or hurricanes, and hurricanes start at 74 miles per hour. So wind speeds at its lowest will be that, but typically you can have greater wind speeds when you see hurricanes. So thankfully, our hurricane season here in Hawaii is almost done. And I don't think we're going to have to worry about any more hurricanes for this year. But let's look at the Saffir-Simpson hurricane scale. And so this, once that storm has reached the hurricane status, so it has winds of 74 miles per hour or greater, that's when it becomes a hurricane, and then it gets a category number. So when you hear Cat 1, Cat 3, or Cat 5, that's what they're referring to. So a Category 1 hurricane has wind speeds between 74 and 95 miles per hour. Typically, the damage that a Cat 1 hurricane will cause is very minimal. You'll tend to experience some coastal flooding. You'll tend to see some vegetation affected, some roads, maybe some infrastructure that was very much in disrepair and needing to be repaired, or areas that are very in low-lying areas. Those types of areas will tend to be affected, but on average, most places will be just fine. If you have a house on the coastline, the storm surge that you'll experience is anywhere between 4 to 5 feet, and we'll talk a little bit more about that in the upcoming slides. But when you start getting up to Cat 2s and Cat 3s, that's when you can see a little bit more damage occurring, because your wind speeds are up to between 96 miles per hour and 130 miles per hour. So, and your storm surge tends to be between 6 to 12 feet. So you're starting to get more rain and higher wind speeds, which will then tend to affect more properties. And definitely streams will tend to be flooded, and majority of the low-lying areas will be submerged in water. Once you get up to Cat 4, this tends to be pretty extreme, as it says there. Your wind speeds are at 131 miles per hour to 155, and your storm surge tends to be between 13 and 18 feet, which is pretty high. And in this case, a lot of buildings will have some sort of structural damage. A lot of roof structures on small buildings will fail and come off, and there will be extensive flooding around coastal regions and near streams, and definitely in low-lying areas. And once you get up to Cat 5s, I hope we never experience a Cat 5 here in Hawaii, because that can be catastrophic. Your storm surge will be greater than 18 feet, and your winds will be more than 155 miles per hour. So majority of the buildings will have significant structural damage. If not, a lot of the weaker buildings will just collapse altogether. You'll have extensive flooding all around the islands here in Hawaii, and majority of the coastal regions will be inundated with a ton of water. not only from the rain, but also from the ocean. So let's look at a global view here. This is looking at the different tracks that the different hurricanes take to date. So this is just a massive compiling of all the information we have about different hurricanes and where they traveled from and where they went to. And as you can see, what I want to show you is the equator is in the middle there, where you have this empty spot. And then above and below the equator, you can see all of the tracks and the colors. The coloring scheme of the tracks refers to what category that hurricane was. So the blue and greens tend to be your Cat 1s and Cat 2s, whereas your red colors will be your Cat 5s. So very strong storms. And as you can see in the Pacific Ocean, majority of the hurricanes are produced in the west side of the Pacific Ocean, over by Southeast Asia, where you have like Indonesia and what is that? The Philippines over there. So all of that is where there's a bunch of warm water, and we'll talk about that in a little later lectures. But that warm water tends to generate a lot of hurricanes during the summertime, as well as over off the coast of Baja California and Mexico. That's where all of the hurricanes that we experience here in Hawaii are generated from. But they pale in comparison to the amount of hurricanes that are generated over by the Philippines. And then in the Atlantic, you can see over by the Gulf Stream and the Caribbean, majority of the hurricanes are created over there and tend to swing upwards following the Gulf Stream, where the Gulf Stream flows at, because there's a lot of warm water over there. And then you can see in the southern hemisphere over by Australia, there tends to be other hurricanes that occur over there, but with less frequency as it does in the northern hemisphere. So that storm surge that I was talking about and the Saffir-Simpson scale tends to create a lot of problems for those properties that like to build their house right on the coastline. So during hurricanes, they tend to bring a lot of wind and a lot of flooding, because that wind will push a lot of that ocean water onto shore. So depending on how strong that wind is, it can push more water. So the higher category you get, the higher that storm surge will be, because you have stronger winds. And so in the figure below, you can see where the mean sea level is at. So that's on average where the sea level is. And then once you get up to the normal high tide, which tends to be about 2 feet higher than the average sea level, and that's on the normal basis. So you see that house there. That house typically is not affected by the 2-foot normal high tide, because the water stays over there. It doesn't go past that mark. But if you have a storm that comes in and it creates a 15-foot storm surge, so let's just say that's about a Cat 4 hurricane, that should be about a 15-foot storm surge. You have to add that 15 feet to the 2 feet normal high tide, so that creates a 17-foot storm surge. So that 17 feet of water that normally is not there will be pushed onshore by those strong winds and flood that house there. So even though that house is set back pretty far from the coastline, if you have a really large storm, it doesn't matter where that house is going to be at, it's going to get flooded, right? And because typically these houses that are near the coastline tend to be in low-lying areas, so they tend to flood much more easily. And about 90% of the deaths associated with hurricanes are the result of storm surge, because it can come on shore very, very quickly. So here's just a list of some of the more destructive hurricanes that we've had throughout the years, and in the United States. And as you can see, in 1959 we had Hurricane Dot here in Hawaii. That was pretty devastating. I believe it hit Kauai and Oahu. I could be wrong though. But definitely 1982, Hurricane Eva, that one hit Oahu. It was pretty strong. And then in 1992, we had Hurricane Iniki that hit Kauai. And that was pretty devastating for the residents on Kauai. But you can see that there have been other pretty devastating hurricanes across the country. You can see in 2005 there was Hurricane Katrina that affected Louisiana and Florida. And just last year we had Hurricane Maria that affected Puerto Rico in the Caribbean. So we've had some pretty strong ones that have really affected a lot of people, not only because of the storm surge, but because of the amount of damage that these hurricanes caused. Hurricane Katrina was a Cat 5 when it made landfall, so it made a lot of damage when it hit. And so let's step back and look at the different regions of the ocean, because the tropics is where you tend to see a lot of the hurricanes created. And so the tropics are the orangey area surrounding the red region, which is your equatorial region. So your equatorial region, while it is warmer, it tends to have a lot of cloud and rain cover. And on either side of that is your tropics, and that's where you have your equatorial currents, which we'll talk about in the following chapters. You tend to see rough seas, you tend to see hurricanes created in here, and you have strong winds. Next, you have the subtropical regions, which are in yellow, and this is where you tend to have high pressure areas. So your tropical regions are your low pressure, where your subtropicals are your high pressure. So you don't see a lot of rain or precipitation in these areas. You tend to see higher evaporation rates because you don't have a lot of cloud cover blocking out the sunlight. So the sunlight that does come down tends to evaporate the water more quickly, and you don't see very strong winds in this area. So you tend to see weaker winds and weaker currents. And then on either side in the green, you see the temperate regions. These are typically characterized by strong westerly winds, so they're going in the opposite direction now. And you tend to see a lot more precipitation because this then converts back into a low pressure area. And during the wintertime, you see pretty large storms occurring. And then on either side of that, in the blue, you have your subpolar regions, which tend to be covered in ice majority of the year. You do experience a lot of rain, heavy precipitation in this area, and you experience colder temperatures because it is in the polar region, so it's not getting as much solar radiation being absorbed into the land. And then lastly, the white regions represent your polar regions, and that's where you have high pressure, so you tend to experience colder, drier conditions. You typically don't see any sunlight during the winter time, and you tend to see majority of your sunlight during the summertime because you are just that far up there. A lot of that solar radiation is lost during the winter time. And then in the polar regions, there is a process to which sea ice forms, and this sea ice forms directly in the seawater, so it doesn't form on land and then is transported into the ocean. So the process starts off with these small hexagonal crystals, which is photo on the top there. And those crystals continue to accumulate and eventually will turn into slush, which you see in the next image below the top one there. And that slush then is broken into pieces by the wind and waves. And eventually those pieces come together in a disc shape, which is known as pancake ice. And so that's the image that you see, the third image on the right hand side there. And that pancake ice then merges together into larger ice flows, which you see as a fourth image. You can see it's broken apart though, but it makes much larger, more angular shaped ice pieces. And then those ice flows eventually will merge together to create pressure ridges. So that last image down there, you can see these huge ice sheets are pushing up against each other and breaking each other apart, and creating this little ridge in between them. So you can essentially see where the two large ice sheets are interacting with each other. And then you have icebergs that form in the polar regions. And so icebergs are just floating ice that have broken away from a glacier. These icebergs, as you should well know, majority of the iceberg lies beneath the ocean's surface, and that's due to density. So even though the density of the ice is less than surrounding water, because of how large that ice piece is, it sits a little bit lower in the water. So that's why when you see an iceberg, you only see a small portion of it at the top, and then you tend to see much more of it at the bottom. And icebergs tend to be distinct from sea ice because icebergs are created on land and then eventually make their way into the ocean, whereas sea ice is created in the ocean and stays in the ocean. Icebergs are pieces that have broken off of the glacier and gone into the ocean, and they eventually melt, but it can take several years before an iceberg fully melts, and that's partially because it doesn't travel very far or very fast, and even though the surrounding water is melting the ice, because of its large size, it can take quite a while for that iceberg to melt. And this is different from shelf ice. So shelf ice, if you have a glacier that extends over the ocean and it starts to thin slightly, and then part of that shelf breaks off, you have what's known as claved icebergs. And so they tend to be more square or rectangular in shape versus your icebergs that come off of the glacier tend to be more angular, more triangle or diamond shaped, where you have majority of it lying below the ocean surface. These ones tend to have flat tops and can be pretty thick, but in comparison to the rest of the glacier that's on land, the part that's resting over the ocean tends to be thinner. And lastly, you can get energy harnessed from the wind. And so on the image there, you can see the areas where you have greater wind speeds. And so companies who try to produce energy from the wind, so they have windmills and whatnot, tend to look for areas where they have greater wind speeds. So not everywhere in the ocean you can see has very strong winds. And so when they are trying to harness the energy from the wind, they will put out turbines out into the ocean to take advantage of the stronger wind speeds that they have. And as you can see, over near the Antarctic continent, as well as in the northern hemisphere, where you have North America and Europe and whatnot, you tend to see stronger winds up there. And so that's just one way that you can use wind towards your advantage. Whereas in a hurricane, tends to be a disadvantage to have a hurricane near you. Anyway, so this was chapter 6, air-sea interaction. Hope you learned a little bit something about the atmosphere and how it interacts with the ocean. Next chapter, we will be talking about, I think it's currents, maybe. Anyways, stay tuned for chapter 7. All right.